Hi, my name is Changsuk Noh. I work in Gyeongbuk National University. First of all, I would like to thank the organizers for giving me an opportunity to present this work at ICQC, and I also apologize for not being able to attend in person. So today I'll talk about quantum illumination with definite photon number entangled states. So this work was done in joint collaboration with Dr. Soo-Young Lee at ADD and Dr. Chang-Hyuk Lee at CRIS. Is published in this work if you want to have a look. So outline is simple. I'll give a brief introduction to quantum illumination for those of you who are not familiar with the concept. And then I will present our work, recent work. Okay, so what is quantum illumination? So the task in quantum illumination is to detect, it's like a radar. It's not fully radar, but it's just to detect whether the object is there or not. Okay. We assume that the object is embedded in a noisy environment. So then the noisy environment is just a thermal environment. Yeah, and we assume that the object is far away, so there's large amount of loss. So how do we model this? First of all, we model the object target with a beam splitter. It's a small reflectivity or no reflectivity at all. So when eta is 0, there's no object. When eta is very small, the object is there. And on the beam splitter, we have two inputs. One from the signal field that we are sending to detect the target, and the other port has a thermal light, which is properly normalized so that irrespective of the values of eta, we always get the same thermal light going into the detection system. In quantum illumination, we use entangled quantum light, entangled quantum state, and the part that goes to the target is called the signal mode, and part that remains in the lab is idler mode. And we perform a joint measurement on the idler mode and reflective mode together. When there is no object, when eta is 0, the state is a thermal light and the idler mode, that's rho 0. When there is a little bit of signal reflected, that part is rho 1. So, and we perform a correlation measurement of this. And we ignore this part. Yep. So the task for us is to distinguish between two density operators. So it's quantum hypothesis testing, binary quantum hypothesis testing. To do this, we need a decision strategy, which amounts to a POVM, the most general measurement. We call it E naught at E1. E naught is for us to decide when that the object is not there. 1 is for us to decide when the object is there. Well, so we'll say the object is there, and it's a POVM. So they add to 1. And then we have 4 cases. So this is when the object is not there, this column. This column is when the object is there. And this is for our decision. We choose to say it's 0, that it's not there. We choose hypothesis 1, which is that the object is there. So these are 4 conditional probabilities. Among these, we have 2 error probabilities. So when the object is there and we say it's not, so we miss the object, so it's a missed probability. When the object is not there and we say it's there, so it's a false alarm probability. So these 2 error probabilities are what we want to minimize, but they're not independent. So there are largely two different strategies to minimize the errors. In this quantum illumination, we concentrate on the Bayesian case, where we minimize the total error probability, where the pi's are the prior probabilities that the object is not there or there. Okay. It's not too difficult to show this, but the optimal measurement scheme, the POVM, gives us the minimum error probability to be this, where so now I'm talking about m copies of so we are sending m copies to the target, and there are m idler copies as well. So that is a trace norm, and that's the norm of the operator defined, and this is called the Hellstrom bound or minimum error probability. From now on, we'll just assume the symmetric case, but this is not necessary. But this is just to help ease the equations involved. Okay, so this quantity is difficult to calculate. If you could calculate this, then everything's solved, but they are difficult to calculate. And people usually resort to a quantum Chernoff bound or a quantum Bhattacharya bound, which are the upper bounds to the minimum error probability. So quantum Chernoff bound is the more tighter one, and it was proved in this work. If you're interested. And what we see here is the error probability decreases as exponentially with m number of copies, and there's some factor involved which we call Chernoff error exponential error bound. Error exponent. Yes. So this is the quantum Chernoff bound error exponent, which is given by this quantity. So it involves, I mean, there's a logarithm, but it's a minimization of all of this quantity, where this quantity is the trace of the rho naught to the power of alpha times rho 1 to the power of 1 minus alpha. What's nice about QCB, the Chernoff bound, is that it's known to be asymptotically tight. That means as m increases, we know that the equality holds. Because of the minimization or optimization, this might be difficult to solve sometimes, and then we resort to a quantum Bhattacharya bound, which is when alpha is half, so it's the square root of rho naught, square root of rho naught. Okay, so just remember this thing. So minimum error probability is upper bounded by the QCB, which is upper bounded by the QBB. Okay. So now let's look at illumination. Because we know how to calculate quantum Chernoff bound for Gaussian states. So 10 arrow, that's Shapiro group, they have worked out the Gaussian state quantum illumination, where they consider the coherent state for the classical case, where there's only a signal mode going in without the ideal mode, and the two-mode vacuum for the quantum case, quantum illumination. So first, the classical illumination with the coherent state, single mode. In this case, the quantum Chernoff bound, QCB, is known to be the same as the QBB. It turns out to be the same as the QBB. And the quantum Chernoff bound is actually calculable nicely. And it's this. So that's the CB, the Chernoff exponent. So eta squared times ns, that's the signal photon number, times this thing that depends on the thermal photon number. When thermal photon number is small, we have essentially eta squared times ns. When thermal photon number is large, this thing is divided by 4 times n thermal. And that's the coherent states error exponent that we will keep in mind. So this is useful to keep in mind. So that's proportional to signal photon number and inversely proportional to the thermal photon number. That's the error exponent. In quantum illumination, we use two-mode squeezed vacuum state, which is a Gaussian state. So we can describe it using a covariance matrix, which is defined like this, but that's not important. So diagonal elements, they are given by essentially the signal photon number. And off-diagonal ones, they describe the correlations between the two modes, and they're given by this quantity. It turns out that this quantity is the maximum correlation value allowed by quantum mechanics under the given diagonals. Okay. So that's the maximum correlation allowed by quantum mechanics. The classical limit is 2ns. So 2ns. So if you compare these two, then you can conclude that the large non-classicality requires a small signal photon number. It's a little bit unintuitive, but this will show up in our results on quantum illumination. Okay, so this summarizes the quantum illumination of the paper. So that was the error exponent we saw just now. And if you calculate the quantum Bhattacharya bound, not the Chernoff, but the Bhattacharya bound, you see that this is this thing, which is 4 times larger than the error exponent for the coherent state. So that's what's shown here. So here, the thermal photon number is 20, and the signal photon number is 0.01, small. So that's large and small, and kappa is eta squared, so 0.01. Blue curve is the coherent state. Red curve is the two-mode squeezed vacuum, and you see here it's about 4 times the difference. That's a log scale. So that's one conclusion. So error per exponent, because this is a Bhattacharya bound, which is upper bounds the Changsuk bound. So it's at least 4 times larger than the JCS, the classical exponent. And that's up the 6 dB advantage in the literature. On the right-hand side here is when everything is the same, but the signal photon number is increased to 1. And in this case, the advantage disappears. I mean, it diminishes. And if we increase the NS further, it disappears. So that's another conclusion, which agrees with the what we said about the correlations in the two-mode squeeze vacuum state. One other ingredient before we move on to our work is we need to discuss quantum estimation just a little bit. So what's the difference between quantum illumination and quantum parameter estimation? Quantum illumination, we try to distinguish between the reflectivity, 0 and eta. In quantum parameter estimation of eta, we try to estimate the value of eta. But if we know the value of eta accurately, then we can certainly distinguish between 0 and eta. So they're related. And that's what we'll see a mathematical relation for that as well. An important figure of merit in quantum estimation is quantum Fisher information, as many of you will know. So inverse quantum Fisher information is a lower bound to be variance in the estimated parameter. Because Fisher information is additive, that means basically we are talking about local strategies. So remember we had m copies, and the Changsuk bound is for when a joint or global measurement is performed on n copies on the same altogether. Whereas this one is because of additivity, which is it has to be local. It has to talk about local measurement strategies. And in this case, Sanzero, they have in this paper showed that the two error probabilities, false alarm and the miss probabilities, they scale like this with exponentially with m. Where this plays the role of error exponent, and FQ sort of plays the role of NS over N thermal type of thing. And they also showed that when the signal photon number is small, the maximum Fisher information is only twice the quantum Fisher information of the coherent state. So if you use entangled state, twice of this is the limit. This can be seen here in if you calculate the quantum Fisher information for the coherent state and the two-mode squeeze vacuum state. This is an approximate one when NS is small, I think. And if you compare this, when N thermal is large, then we see that this thing is twice as large as this thing, if we can ignore 1 here. Okay, so that's one limit we can get here. Okay, now we are almost ready to come to our work with the definite photon number entangled states. So this one was first studied in quantum illumination case by Suyong Lee in this paper and others. This is n photon numbers shared between the signal and the ideal mode. It's a general state. It's a non-Gaussian state, so it's difficult to calculate the QCD, the Changsuk bound. So they calculated it numerically and optimizing this. So here's an example. For choosing n equal to 4, they numerically optimized the Fisher information over Cn for our setup. And this their H is our F, so that's the Fisher information for 4 photon entangled states. That's for the coherent state. Don't worry about the TMSV state, the two-mode squeeze vacuum state. Just look at the black one. That's the N thermal on the x-axis. So the ratio between the two can go up to 2 and it decreases, but it doesn't go below 1. So there is quantum advantage in using this. That's what they showed. And another thing that they showed is for a particular measurement setup. So quantum Fisher information is for an optimal setup, where then this is just a general setup. And in this case, using some assumptions, a probability assumption, they show that the SNR, which plays the role of visual information in this measurement setup. So when we do this, the 4-photon entangled state, optimized one, has a very large SNR. SNR that grows with the ensemble, whereas the coherent state is SNR that drops down. So it's like going up here. So we wanted to calculate this without the separability assumption. So that was our main motivation. But then we found that there was something here to talk about as well. So let's talk about this. We are going to redraw this black line using a log scale of n so on. And that's what we did here. So that corresponds to the black curve. Don't worry about this. This means that the signal photon number is 2 here. And whereas n equal 2. So half of the total energy is sent to the signal mode. Yeah, so that's if we do local measurements, we get 3 dB max. That's two times in the error exponent. That's what we're seeing here, as we see. But we can do better, right? So we know that the total energy is fixed to 4, total photon number is fixed to 4. So if we send all 4 in the coherent state to the signal mode, then the quantum advantage completely disappears. Okay, so quantum advantage depends on the signal photon number for the coherent state we choose, and to have a fair comparison between this DPNE state and the coherent state, we need to compare them for the same signal energy. So that's what we did. If we do that, then we see that the coherent state always has a higher SQ, thereby error exponent than the 4PE state. Don't worry about the TMSB. And if you calculate the signal photon number, you see that it decreased from 4 to just below 3. So when it's 4, it's the same. When it's 3, it's the same. But here, its coherent state is better, which you can calculate using this formula. Okay, so that's one. And then we asked, what about other values of n, the total number of photons? So we varied n while fixing a value to a particular one and so on, but that's not an important one. If we increase n, initially the gap between the coherent visual information and the empty visual information widens, but it sort of saturates out. So that means the difference in the error probability, minimum error probability, becomes insignificant for large enough n. So it's not so. And NF coherent is always larger, so coherent state is always better than the our state, DPNE state. Yeah, so we can conclude that the best DPNE state performs worse than the coherent state with the same signal energy. And I won't talk about this, keep the time. And we also looked at the number difference measurement scheme, the one that involves a beam splitter and the number difference measurement that we saw. Sorry, I'll go back a bit. So this one. So now we're going to calculate this again using exact formula. And what we see is that the coherent and the 4P state give the same result in this case. So the red dots are the coherent state. The blue curve is the 4P state. And they give the same result, same error exponent under this measurement. And another interesting thing we found, another thing we thought was interesting was that the optimal measurement given by the visual information, that is the green curve, and it's almost the same as the blue curve and the red dots. So this measurement is sort of almost optimal throughout the values of n somewhere. And this behavior sort of survives for other values of n as well. So that's the end of my talk, and so I'll summarize. So quantum illumination exhibits 6 dB advantage in the error exponent, 4 times advantage in the error exponent over the best classical scheme. And local schemes, the ones we used for with quantum visual information, they only allow up to 3 dB advantage. And photon entangled states, on the contrary to what we expected, is not useful for quantum illumination. But I'll just like to add one thing. Is this really true? This is what we asked when we were finishing up the project. And we realized that no, it's not, because at some values of NS, the that the photon-number entangled states can perform better than coherent states. And that's one result I'm showing here. So we are working on this now. And so that's the NS, signal photon number, and that's the difference in the Fisher information, quantum Fisher information between our state and the coherent state. So we see that for nth number large enough, we get like 50%, more than 50% advantage in the Fisher information, so error exponent. So yep, that's it for me. So and thank you for listening.